what about on the second half of the path? Let's try to figure out the direction of the velocity and the acceleration vectors here. Well, what would be the direction of the velocity vector?
Down.
That's right. Now, on this portion of the path, just based on your common sense, don't even think about the physics, should the object be experiencing increasing or decreasing speed?
Increasing.
Yeah, we just know from our ordinary experience that as an object is falling, it falls faster and faster and faster. So the speed should be increasing. So what does that tell us about the acceleration vector here?
It's up.
Why?
It's anti-parallel.
Let's go through that step by step. Did we decide the speed was increasing or decreasing?
Speed's increasing.
Now, when the speed is increasing, does that mean that the velocity and the acceleration are parallel or anti-parallel? You might want to go back and look at our previous parallel. That's right. If you look at the horizontal examples that we did before, yeah, so here's our key definitions. When the velocity is parallel to the acceleration, that's when you are speeding up. And when the acceleration is anti-parallel to the velocity, that's when the speed is decreasing, when you're slowing down.
Okay. So acceleration.
So the key things to watch out for are parallel or anti-parallel. When the acceleration is parallel to the velocity, the speed is increasing. And when the acceleration is anti-parallel to the velocity, the speed is decreasing.
Okay.
We were talking about how it's a little bit difficult to interpret the acceleration, but that's the best interpretation we can get for the direction of the acceleration. The best way to interpret it is to compare it to the direction of the velocity.
Okay.
All right, well, let's try this again then. We said the speed was increasing, so what direction should the acceleration be in?
Down.
Right. Notice that you really have to think about each arrow separately. For example, some people might think logically that since the velocity has reversed, the acceleration should have reversed, but it didn't work that way. Just because the velocity acts in one way doesn't mean the acceleration has to act in a certain way.
That was my
Yeah, okay. All right, well, professors know that that's the natural way that people think, so that's a common trap on tests. So we can't just take a guess. There's no alternative to just thinking carefully about each arrow separately. One arrow doesn't necessarily tell you what's happening to the other arrow. Velocity and acceleration are separate. All right, so here we have a case where these are both pointing down. Okay, so that would give us that. The most important thing we saw here is we reviewed that when the acceleration is parallel to the velocity, you're speeding up. And when the acceleration is anti-parallel to the velocity, that's when your speed is decreasing. You were asking me if I could think of an example like this, where you were moving down with decreasing speed. Well, this was not that example, because here you'd be moving down with increasing speed. An example might be if you're, let's say you jump out of an airplane. Well, as you know, after you jump out of the airplane, you'll be speeding up, right? However, how about what happens if you trip your parachute? Well, the parachute will start slowing you down. So at least for a couple seconds, you would be moving down with decreasing speed. So this might represent how someone is moving a couple seconds after they trip their parachute.
Okay.
All right. But in free fall, you would normally be moving down with increasing speed. Gravity is speeding you up. It's when you're moving up that your speed is decreasing. Gravity decreases your speed when you're moving up, but gravity increases your speed when you're moving down. That's why it's a little bit hard to think of a real-life example of this, although it could come up. Okay? All right, so trick question. Which way is this object moving?
I don't know.
Yeah, all right. Until we see the velocity, we don't know. And in fact, it's really hard to interpret this without the velocity, because we can't tell whether this is parallel or anti-parallel to the velocity until we're given the velocity vector. So it's hard to say much about this until we're given the velocity vector. But it certainly does not say the object is moving up. Okay, so hopefully now we have a slightly better idea of how the velocity tells us our speed and direction of movement, and the acceleration basically is describing whether the object is speeding up or slowing down. Now, all of this is a little bit oversimplified because this is only, in 2 dimensions, the acceleration can tell you something else. In 2 dimensions, the acceleration could also tell you whether you're changing direction or not. The acceleration, so basically the acceleration describes, one more way to put this is, I should have put this before. The acceleration describes how the velocity is changing. The acceleration describes how the velocity is changing. That's what we said here, after all. The velocity is the motion. So if you're describing how the motion is changing, you're describing how the velocity is changing. So theoretically, the acceleration could tell you how the speed is changing or how the direction of movement is changing. But in one dimension, you can't really change your direction that much. In one dimension, you're always moving along a straight line, so we're not going to have to talk about changes in direction very much right now. We'll get into that more next week. In one dimension, the acceleration mainly just focuses on how the speed is changing.
Okay.
Okay. Oh, so. All right, so let's describe what do we know about this object.
It's speeding up.
And what else do we know about it? Let's say the speed is increasing.
And then the object is moving up.
Yeah. It's moving up, and the speed is increasing. What do we know about this object?
We know that this object is moving up and slowing down.
Okay, how do we know it's that the speed is decreasing?
Because acceleration is down.
How does that tell us that the speed is decreasing?
Because it's anti-parallel to the...
That's right, good. So we should not think that downward acceleration always means that the speed is decreasing. It's only because it's anti-parallel here. Good. Now here's the case we haven't talked about yet, but this is very important in physics.
Yeah.
What about when the acceleration is 0? Now first of all, if the acceleration is 0, we can't draw an arrow, because the arrow would have to have 0 length, which you can't draw. So this is a case, if the acceleration is 0, you don't draw an arrow, you just say numerically that the acceleration is 0. Well, if an upward acceleration means the speed is increasing, and a downward, if a parallel acceleration means the speed is increasing, and an anti-parallel acceleration means the speed is decreasing, what is there left for a 0 acceleration to mean? Nice.
Well, it's constant,
Yeah. Who's constant?
the acceleration.
That actually was not right. The speed is constant. Parallel acceleration means that the speed is increasing. Anti-parallel acceleration means the speed is decreasing. And a 0 acceleration means the speed is constant. Or really, it tells you that the velocity is constant. In this case, those would be the same thing. But in one-dimensional motion, we can just focus on the speed. So for one-dimensional motion, we'll just focus on this. So what you originally said is that when the acceleration is 0, that the acceleration is constant. That's just not true. If the acceleration is 0, the acceleration could be constant at 0, or it could be increasing through 0, or decreasing through 0. When the acceleration is 0, that tells us that the speed and the velocity are constant. I'll write this down too. Let's write this. Okay, this is one of the most important relations in the class that people really tend to get confused about, so it's very important to make a flashcard about this. When the acceleration is 0, the velocity is constant. When the acceleration, let's write that again someplace else. When the acceleration is 0, the velocity is constant. So what does it mean when the acceleration is not 0?
Velocity is not constant.
Which means the velocity must be changing. Good. This is a very important set of relationships to be very comfortable with. A 0 acceleration is a synonym for a constant velocity. And a non-zero acceleration is a synonym for a changing velocity. So what does that tell us if the acceleration is 0? It means the velocity is constant. Yeah, sure. And the key thing is to recognize that the point of this is to show that these two are synonyms for each other, and these are synonyms. Oops. If the acceleration is 0, then the velocity is constant. What does that mean? Well, we know that the velocity is the speed and direction. So if the acceleration is 0, that tells us that both the speed and the direction are constant. But we're not going to focus too much on direction for one-dimensional motion. That'll be more important for two-dimensional motion. For one-dimensional motion, we're mainly focusing on the speed. And what does it tell us if the acceleration is not 0? That means the velocity is changing, which means either that the speed is changing, or that the direction of movement is changing, or that both of them are changing. All right, however, for one-dimensional motion, again, we're really going to focus on how the speed might be changing. It's not until we get to two-dimensional motion that we'll focus on direction too much. So that's what these mean.